Hello again, Physics 30s. In today's lesson, we're going to look at a second source of a magnetic field, that being an electromagnet. We'll also briefly talk about a scientist and how he made an accidental discovery regarding the relationship between electricity and magnetism. And I'm going to introduce you to the hand rules, which you can use to predict the direction of a magnetic field depending on the direction of current. Learning outcomes, as identified by the Physics 30 program of studies, are 1. Describe how the discoveries of Oersted and Faraday formed the foundation of the theory relating electricity to magnetism. 2. Describe qualitatively a moving charge as a source of a magnetic field and predict the orientation of the magnetic field from the direction of motion. And 3. Compare gravitational, electric, and magnetic fields caused by permanent magnets and moving charges in terms of their sources and directions. And today we're going to focus more on the moving charge part. The scientist I mentioned is Hans Oersted. What he did is he accidentally discovered a relationship between electricity and magnetism. The reason I say accidentally is because he did not actually intend to do this. He actually wanted to show that there is no connection between electricity and magnetism. I'm going to briefly just describe the experiment, or a very simple experiment that he performed where he did make this discovery. So let's say that he gathers all the greatest minds over the world, the greatest physics minds over the world, brings them into a lecture hall, and then tells them, I'm here today to prove there is no connection between electricity and magnetism. His apparatus gets set up as follows. So let's take a straight current carrying wire. And right now, let's not have any electrical current through it. So let's say that the circuit is disconnected at this point. And then we're going to take a compass, and we're going to put a compass in front of this wire. And for the time being, let's say that the compass needle is just oriented vertically upward. Now, what Oersted tells his audience is, I'm going to put an electrical current through this. So I'm going to represent an electrical current with I. An electrical current is obviously electricity. And when I put an electrical current through this is going to have absolutely no effect on the compass needle. If it has no effect on the compass needle, then there is no connection between electricity and magnetism. So he turns the circuit on, he puts a current through the wire, and he puts the current through the wire, the needle deflects. The only way that needle can deflect is if there is a magnetic field that's produced that can cause it to align in the direction of that magnetic field. The needle on a compass would be a magnetic dipole. Magnetic dipoles align at the direction of a magnetic field. So somehow that current is producing a magnetic field, which is causing the compass needle to deflect, and therefore we have our connection between electricity and magnetism accidentally. These two pictures here we'll come back to in a moment. It talks a little bit about the how the direction of current and the direction of the magnetic field compare. But like I said, we'll come back to that on the next slide. What we want to talk about today is a second source of a magnetic field, that being an electromagnet. What an electromagnet is basically it's just a moving charge, or a bunch of moving charges. So for example, if you had a proton that was just moving through empty space, this proton would produce a magnetic field. It's a moving charge. If you had an electrical current with electrons flowing through it, a bunch of electrons kind of side by side, and they're all moving in the same direction, each of these electrons would actually produce a magnetic field. Since there's more electrons, though, they would contribute to a much larger electric field. And that's all an electromagnet is. It's an object that produces a magnetic field, and it does it as a result of charges moving through the object. So typically, the object that we deal with is a conducting wire. A conducting wire can have electrons moving through it. And as I just mentioned, each one of these individual electrons can produce their own magnetic field. When you put them all together, then they produce a larger magnetic field. Now, just before I move on here, I do want to just quickly, again, compare all our different fields. So again, a field is just a region of influence surrounding some kind of an object. A gravitational field is produced by any object that has mass, and it influences other masses. An electric field is a region of influence that surrounds an object with charge. A magnetic field, there can actually be two sources. The one we talked about in the previous lesson, that being a ferromagnetic material. Ferromagnetic, meaning the material contains iron, nickel, or cobalt, or a metallic alloy combination of them, with aligned domains. And the other way we can produce a magnetic field is as a result of either a moving charge or moving charges. Usually we deal with moving charges because the more charges that are moving, the bigger the magnetic field we can get. So that's a pretty big distinction between magnetic field compared to electric and gravitational. By the way, this symbol right here, B, is going to be the symbol we use to represent magnetic field, which we'll get into in the next lesson. In terms of the direction of the magnetic field, now here's where we'll go back to those pictures on the previous slide. It turns out that the direction of the magnetic field is always going to be perpendicular to the direction of current. So if I look at this picture here, in this picture, you have a current that's flowing vertically upward. We use the variable I for current, and that causes the needle to deflect where it's pointing towards the left. Because the current is going vertically upward, the needle points towards the left. There's a 90-degree angle between them. This is if the compass is behind the wire. In the second case here, we have a current that is also going vertically upward. This time around, the needle deflects towards the right. We still have a 90-degree angle between the direction the needle points and the direction of current. And again, the direction the needle points is the direction of the magnetic field. And this is the direction it would point if the compass was in front of the wire. Now, immediately you might be wondering, well, how do I know what direction the compass needle is going to deflect? Is it going to deflect towards the left or deflect towards the right? Because in both situations, the direction of the compass needle is perpendicular to the current. In order to do this, we need to talk about something called the hand rules. The hand rules are going to help us predict what direction the magnetic field is going to be. When I say a hand rule, I literally mean you are going to use your hand or hands to help predict the direction of the field. And we're going to use different parts of our hand to represent different physical quantities. And that's the point of the hand rules. It's going to help us predict the direction of a magnetic field. Now, before we can use the hand rules, we need to know which hand we can actually use. Back in the electric forces and field unit of study, there were two different models of current we looked at. There was one that was called electron flow and one that was called conventional current. And I'll just quickly review it here. Let's say we have a battery. Long end of the battery is the positive terminal. The short end is the negative terminal. Let's put a resistor in here just to slow the current down. The direction of electron flow would just be the direction an electron would move if you put it in the circuit. If I put an electron in the circuit at the very top right here, it would attract towards the positive terminal and repel from the negative one. So my direction of electron flow would be towards the left here. Or if you look at it, the entire circuit, the direction of electron flow would be clockwise, I believe. The direction of conventional current is the direction as if you put a proton into the circuit. If I put a proton into the circuit, it would repel from the positive terminal and attract towards the negative one. And that would result in a conventional current direction, I. That would be, I think that is going to be clockwise. I think the electron flow is in a direction that is counterclockwise. The current is in a direction that is clockwise. Yeah, I think that's right. Yeah, so current is in a direction that is clockwise. CW, electron flow in a direction that is counterclockwise. Sorry about that. Just wanted to make sure I corrected it. Okay. Now, depending on whether we're looking at the electron flow model or a conventional current model, we need to pick a correct hand. If we're talking about electron flow, we're going to start off by using our left hand. If we're going to use the conventional current model, we're going to start off by using our right hand. There are going to be two hand rules we look at today, and they're each going to apply to like different situations. The first hand rule applies to scenarios where you have wires that are straight. Looking at the diagram here, I can see a straight current carrying wire. So if you look at this picture on the right hand side here, this wire is just directed vertically upward, and I have current that's moving through that wire that is directed vertically upward as well. I'm going to change the pen color so you can actually see that. Now, the way to apply the first hand rule is, first things first, in the diagram right here, we have I. I is conventional current. Conventional current is the right hand. You start off by taking your thumb and you point it in the direction of the current. I find it helpful to use a pen or a pencil just to represent the current carrying wire. So in this case, I put your pencil so it's perpendicular to your desk and it's facing upward. And just envision like current that's directed vertically upward out of your pencil or pen. And what I would do is I take my thumb with my right hand and I point it in the exact same direction of the current. What you then want to do is you want to take your fingers and you want to wrap them around your pencil. And you want to look at what direction your fingers curl. So if you take your fingers, if you have your thumb pointing upward, and then you curl your fingers around the actual pencil, you can kind of see from the picture right here like how your hand should look. Now, I'm going to draw a circle to represent the actual magnetic field. So let's draw the magnetic field like this. What I want to do is I want to look at what direction my fingertips are pointing, because that's going to tell me what rotational direction the magnetic field is. If you look at this from a top view perspective, the curl of your fingers should be in a direction that looks like this. If viewed from a top view perspective, I believe that direction would be counterclockwise. So the curl of your fingers tells you what the direction of the magnetic field is. One other thing to note here is if you look at the actual magnetic field lines surrounding the wire, the closer you are to the wire, the closer the field lines are together. The further you get away from the wire, the larger the spacing gets, which just means that the magnetic field gets weaker the further you get away, which I think is pretty intuitive. Okay, so that's the first hand rule. We'll come back to it later when we talk about a few example problems. The second-hand rule applies to a different type of wire. Instead of the wires being straight for the second-hand rule, we apply it to situations where the wire is looped or it's coiled. We have a special name for a device where you have a bunch of wires that are looped around or curled around, and we call that a solenoid. And the second-hand rule is going to apply to this situation when we deal with solenoids. Now, if you look at the actual picture here, and we'll talk about how we can predict the direction of the magnetic field. If I look at the magnetic field inside of the solenoid, the magnetic field inside of the solenoid is pointing towards the left. The other thing to note there is the spacing between the magnetic field lines inside the solenoid. The spacing is equal or even. If the spacing is equal or even, it means the field is uniform. So this is actually a really, really good way to get a uniform magnetic field. Probably even better than looking at between the poles of a horseshoe magnet, or if you had two bar magnets facing each other, looking at what the magnetic field would be like closer to the center of the wire. So this would be like our parallel plate equivalent for getting a uniform field when talking about magnetism in comparison to electricity. Okay, so how do you use this second-hand rule? The parts of your hand are going to represent different things in this situation. So for the first-hand rule, your thumb represented current and your fingers represented magnetic field. We're going to switch that around now. Your fingers are the thing that can curl, and that's the wire. So this time around, your fingers are going to curl in the direction of the current. Now, you need to be careful in how you actually curl your fingers. And what I would do here is, if I want to figure out, like, how do I know the direction the magnetic field is towards the left? What I want to do is I want to look at where the current is first entering the loop. Okay, so the current first enters the loop on this side right here. Now, when I look at this, the loop curls over top of these magnetic field lines. What I would do is I would take your pencil and I would curl your fingers, but curl your fingers so that they are curling over top of the actual, over top of your pencil. If you curl them over top of your pencil, then you should have your thumb pointing towards the left-hand side of the page. And it's your thumb that represents the direction of the magnetic field. So once again, what you want to do is to correctly identify how to curl your fingers, because you can curl your fingers so they go over top of your pencil, or they come in from behind. Look at what the current is initially doing. And what I can see right here is that the current is initially wrapping over top of like the actual magnetic field. Again, we'll come back to this in an example problem to clarify, and that's going to tell you how to properly wrap your fingers. With a solenoid, there are a few ways you can increase the magnetic field intensity. Ideally, what we want to make that electromagnet, that solenoid, as strong as possible. And a few ways to do this would be, one, increase the number of loops within a specific region. If I go back to this picture right here, and you like really, really tightly wrap these loops around, it's like they're really, really like closely packed together, as opposed to having like space between them. Most solenoids don't have any space between the wires. They're completely densely packed together. The reason being is if you have them densely packed together and you put a current through it, then you have a lot of electrons in a certain area. So the number of moving electrons in a certain area or volume is really big. The more moving charges you have through an area, the larger the magnetic field you're going to generate in that area. So that's why we want to make the spacing between the loops smaller. And we can make the spacing between the loops smaller by increasing the number of loops. Two, we could just simply increase the current of the wire. You could do that in a couple of ways. One, you could hook it up to a battery that has a larger voltage or potential difference, or you could decrease the resistance of the wire. Both of them would result in having a larger current. The third one is we can actually combine both our permanent magnet and our electromagnet together. Oftentimes what you'll see is these loops of wires, this solenoid wrapped over top of a bar magnet. So the picture on the left-hand side right here, what we could do is we could take these loops of wire and we could actually wrap them around a bar magnet. What would happen then is if you wrapped the wire around the bar magnet and you turned on the current, well, in this case right here, it shows a magnetic field that's being directed towards the top of the page. So again, we'll use B to represent the magnetic field. All the domains inside that permanent magnet would align in the same direction of that magnetic field. And then what you'd have is you'd have a magnetic field from the bar magnet and the magnetic field from the solenoid working together. So you get a really, really strong magnetic field. If you wrap this coil around the bar magnet, and initially, let's say the domains were unaligned and the external magnetic field caused them to align, you would actually induce polarity on the bar magnet, which means that you would create a north and a south pole. Now, our rule still has to work, where you have the field lines going out of the north pole and into the south pole. So if I look at my diagram here, at the very top, the solenoid produces a magnetic field that is leaving the solenoid at the very top, and it's going into the solenoid at the bottom. So your magnetic field lines have to go into a south pole, and they have to exit from a north pole. Whatever direction your thumb points, that's the direction of the magnetic field, and that is going to be the direction of an induced north pole if you do wrap the wire around a ferromagnetic core. All right, so let's look at a couple of examples where we can actually practice using the hand rule. This is so much easier to do if I actually was in class and could demonstrate this, because you could see what I was doing with my hand. But we'll just have to do the best we can since I don't really have a way right now of like putting a video in showing me how to use the hand rules, nor do I want to do that either. Okay, so we have current flowing from A to B. I'm just going to change the color of the pen here. Let's go to red. Now, immediately when you see that word current, that is conventional current that is going to tell you need to use your right hand. In both these problems right here, we have current that is flowing from A to B. So we'll just quickly sketch this. So we have current that's going from A, and it's moving in from A, and it's leaving to B. Moving in from A, going to B. Now, for part A, again, the trick you want to use right here is you want to see how the wire is wrapping. Is it wrapping from behind the solenoid, or is it wrapping over top of it? Like, what's it initially doing? And if you look right here, it looks like the wire is wrapping in from behind. So what I would do is I would take your pencil and I would take my right hand, because we're dealing with current, and what you want to do is you want to wrap your fingers in from behind the actual pencil, and that's going to represent your magnetic field direction. Sorry, not magnetic field direction, your current direction. So I'll say current, which is going to be represented by your fingers. We want to curl from behind your pencil. pencil or pen. I'll say pen here. Now, if you take your fingers and you curl them in from behind your pencil, what you're going to have is your thumb is going to point towards the right. Your thumb is the direction of the magnetic field. So that's the symbol B. So your thumb would point towards the right. So if your thumb points towards the right, that is also the direction that you're going to induce a north pole. So on this picture right here, if your thumb points towards the right, it means the field lines have to exit from the right-hand side, and field lines only ever exit from the north pole. So the right end's the north pole, and the left end would be a south pole. Okay, and that's the direction of your induced north pole. For the second one, the difference is if you look at what your current is initially doing, this time it's wrapping over top. Over top of the wire. So what I want to do is I want to take my fingers and this time, take your pencil or your pen, and this time you want to wrap your fingers over top of the pencil. So I'm going to say curl over top of pen. When you do that, the magnetic field, which we'll use the variable B to represent, is going to be represented by the direction your thumb is then going to point. If you wrap your fingers over top of your pencil, your thumb is then going to point towards the left. Thumb points towards the left. That's the direction of your induced north pole. Left end's north, right end is south. Now, the problem doesn't ask me to actually draw the magnetic field lines, but I'm going to show you what the magnetic field lines would look like here. Let's use B as an example. So what I'm going to do is I'm going to start at the north pole right here. And again, my rule for field lines is out of the north into the south. So I draw my field lines coming out of the north. They loop around. Make sure when they're looping around on the outside here, they do not pass through the inside of the solenoid. They have to loop around on the outside. So we have out of the north into the south. And then we go through the solenoid, which also has a ferromagnetic core, like that. And we can do the same thing here. We can then loop. But this time we can increase the spacing because the further you get away from the solenoid, the weaker the field gets. And then once again, we can just go through here and form a closed loop. Let's get some symmetry here. So we can start at the north pole here and then go out of the north pole. Again, when you're looping around, do not go through the solenoid. Back into the south. Oops. So much for my horizontal line there. We'll do one more, and this should be out of the north, go all the way back into the south. I want to try to show these lines as parallel as possible and as equally spaced as possible too, because the magnetic field inside of the solenoid is supposed to be uniform. And that's a key characteristic of a solenoid, is it gives you a uniform magnetic field. All right, so that's the second-hand rule applied to a solenoid. Second example, we're now going to look at the first-hand rule to predict what direction the compass needle is going to point. All right, so the first one, A, deals with electrons. And the instant you see electrons, this tells you what hand you need to use. You're going to use your left hand. Left hand, And what I have is my electron flow is directed towards the bottom of the page. So what you want to do here is you want to take your thumb, your thumb is going to represent the direction of the electron flow, and that's going to point downwards. What I would do is I'd hold your pencil on your desk so it's perpendicular to the desk, so it's just standing up. And then I would take my thumb, and then I'm going to point my thumb down towards your desk, and then with your left hand, you're going to curl your fingers around your pencil. And that's going to represent the direction of the magnetic field. So that's your curl of fingers. Okay, now to identify the direction right here, so if you do this, if you take your pencil and you point your thumb down with your left hand and curl your fingers around it, well, let's draw a circle to represent the magnetic field. So if I draw the magnetic field here, this represents the curl of your fingers. If you look from a top view perspective of like your hand, it looks like my fingers are curling in a direction that would be counterclockwise. So on the circle right here, I could draw counterclockwise with arrows that look like this. So in front of the compass, the magnetic field is right. On the right side of the compass, it's going to be directed in a direction we're going to call into the page. And then behind, it's going to point towards the left. Now, that's a little bit confusing to look at. So let's change the perspective that we want to look at the wire here. So let's say this is my eyeball at the very top, and I'm looking straight down at the actual wire. What I'm going to do is I'm going to draw a cross section of the wire from a top view perspective. So a cross section of the wire from a top view perspective would just be a circle. Now, inside the circle, I want to use some kind of notation that's going to indicate what direction the current is going. Now, the current can go in one of two directions. It can either go away from you or it can come towards you. Now, we like to use different words for this. If the current is coming towards you, we say it is coming out of the page. If a quantity is coming out at you, we use a little tiny dot to represent that direction. If the current was going away from you, like it's going into your pencil, we refer to that as being into the page. The symbol used to represent that is an X. Now, there's a really easy way to memorize this. You can think about like firing an arrow. So let's say we have like an arrow here. The arrow has two parts. There's like the arrowhead. Well, I shouldn't say two parts, but two parts of interest. You have an arrowhead and this back part right here, which I think is called like the fletching, something like that. Now, if that arrow was coming at you, what you would see is you would see the arrowhead and just like the point of the arrow, the little tiny dot representing the point of the arrow that's coming at you. If you viewed this from behind, like the arrow is going away from you, what you would see is you would see the back of the fletching, which would appear as an X. So if a quantity is coming at you, you use a dot. If it's going away from you, we use an X. Now, going back to this problem right here, the electron flow is going from your eyeball. It's going away from you. So the way we would represent this is with an X here. Now, what I'm going to do is I'm going to draw a circle around this to represent the direction of the magnetic field. Okay, so circle representing the magnetic field. And again, from your top view perspective, if you have your left hand and your thumb is pointing down towards your desk and you look at the curl of your fingers, the curl of your fingers is going to curl in a direction that is counterclockwise. I can represent counterclockwise with directions at 4 points here. Now, if you look at the picture from like that perspective, what's happening is we want to know what direction the compass needle is going to point if you put the compass in front. Now, based on my picture I have right here, so I'll just go back to different color. This side right here is the front of the compass, or not the compass, front of the wire. This side right here is the back. So what I want to look at right here is in the front, what direction is the compass needle, is the magnetic field pointing? Whatever direction the magnetic field is pointing, that's going to be the direction the compass needle deflects. So at the very top right here, well, the compass needle's, the magnetic field's pointing towards the right. So that's going to cause the compass needle to point towards the right. Now I'm going to add a bit more to the magnetic field. I'm just going to draw one other circle. So the further you get away from the wire, the bigger the magnetic field gets. So I want to really make the spacing big between this one and the next circle. So you have some concentric circles. The spacing should be getting bigger. So from a top view perspective, this is what the magnetic field would look like surrounding that current carrying wire. All right, on to part B. First things first, deal with like, well, which hand you need to use. So this one right here talks about current. Current is going to be represented by your right hand. Oh, let's go back up here again. B, curl of your fingers from that top view perspective was counterclockwise, CCW. Okay, now this time around we have current. So current we're going to represent with I. And your current, which is represented by your thumb. It also points vertically downward. And we want to figure out what the direction the magnetic field is, which is going to be represented by the direction our, our fingers are going to curl. Curl of fingers. Okay, so what I would do is take your pencil, make sure it's upright on your desk, and you want to take your right hand this time. You want to take the thumb of your right hand and you want to point it down towards your desk. Then take your fingers and then curl them around your pencil, which is going to represent the wire. So if I do that and draw a circle representing the actual direction of like the curl of my fingers, so this time around, the curl of my fingers from that top view perspective, I believe should now be pointing in a direction that's going to be clockwise. So we'll put CW. Now let's do this perspective from the top view, from like a top view perspective again. So let's say if my eyeball is up here and I'm looking straight down on the wire. So we'll draw a little circle that represents the wire. Once again, the direction of the current is being directed away from you. So we'll use the X to represent the fact that it's going into the page. And then we'll start to draw the magnetic field lines here. So your magnetic field lines are circular around this wire from a top view perspective. And this time around, the curl of your fingers is in a direction that is clockwise. We'll draw that second circle right here as well, just showing that if you make the spacing bigger, the field's just getting weaker the further you get away. Now, in terms of the direction that the compass needle points, so once again, this is the front of the compass, or sorry, front of the wire. This is the back of the wire. Now, in this problem right here, it shows the compass is behind the wire, so that's at the back. Now, if we look at what's going on at the magnetic field at the back, well, the magnetic field at the back is pointing towards the right. The compass needle is a magnetic dipole. Magnetic dipoles lie in the same direction of the magnetic field. So in this case right here, the compass needle is also going to deflect towards the left. And that's how we apply the second-hand rule to figure out what direction the magnetic field is from the direction of current. So you can now practice the first and second-hand rules, along with like drawing magnetic field diagrams, by completing the assignment called Electromagnets. Talk to you later. Bye.